where the energy is much, much lower. And when we go there, it turns out inside there, the universe undergoes a big crunch. Okay? So for any observer, any typical observer living through this whole cosmological history, there's an incredible symmetry between the beginning. The whole picture is almost sort of time symmetric, right? You go singularity, acceleration, excitement, life, love, etc. Acceleration, death, and a singularity again, right? So these, in other words, these degrees of freedom that started off life as ultraviolet, became infrared, will become ultraviolet again at the end. Okay? And we don't understand any of how this happens, but it's another kind of deep unification between long and short distances. Somehow the long and short degrees of freedom are the same. And this is true because of gravity and cosmology and quantum mechanics. It is not true of phonons in a solid. Those degrees of freedom are not, they're not the same as the underlying, they're collective modes of the underlying atoms and molecules, but there's no sense in which phonons are atoms and molecules, right? They're an approximate description at long distances. This is very different in our universe that has gravity and quantum mechanics, relativity. It's something different. Okay, so let's now talk about the gauge gravity unification. So this is something that actually that begins with what might look like the very earliest hint for it is what might look like a dumb thought you could have as a sophomore in college or something. You might think, people tell you that photons are spin 1 particles. There are Yang-Mills theories, but photons are massless spin 1 particles, or gluons, spin 1 helicity 1. A graviton is a spin 2. So why can't the graviton just be 2 photons on top of each other? Okay, so this is a great theory, right? So after all, if I take 2 photons going this way, then they look an awful lot like they have the same spin. It's the massless particle moving this way, and it has angular momentum too. So this makes you think that somehow gravity should be like 2 copies of a photon. And of course, literally that theory is ridiculous because there's no force that's keeping the 2 photons next to each other all the time. And if you beamed your laser beams a little bit sideways, it would no longer look like a graviton. Okay? But nonetheless, there is something to this idea. In string theory, for example, this is exactly, there's something very much like this, because gluons, photons and gluons are associated with little loops of open string, whereas particles like gravitons are loops of closed string, and there's really a precise sense in which a closed string is like 2 open strings glued together. Okay, so both at the level of just looking at the spin of these particles, closed is open squared, gluon squared is graviton, closed strings are open string squared, gravity is like Yang-Mills squared. Okay, so at this very cartoon level. And in fact, in the last 10 years or so, and actually goes back to a work done by, it had its origin in work done by string theorists 30 years ago, but has been since understood as a very general property just of gravity and Yang-Mills theories in any number of dimensions. Has nothing to do with any details of any extra details. But it's an example of a hidden kind of remarkable relationship between different theories. If you look at the scattering processes involving gravitons, there's a very precise sense in which the scattering process involving gravitons can be computed instead by scattering involving gluons and squaring them. And it's not exactly squaring. You have to interpret the squaring a little bit. There's a little bit of a dictionary to mean exactly what you mean by squaring, but it's still an utterly amazing fact that's totally unobvious. Okay? If you stare at the Lagrangian for general relativity, it's some horrible, complicated, terrible mess. Even this Lagrangian for Yang-Mills doesn't look so great. Even calculating these amplitudes by hand using the textbook rules is impossibly complicated. You would certainly never guess, just staring at that there's any such relation at all. And yet, there is such a relation. So that's an example of a hidden unity, right? There is no reason these things had to be the case. And yet, there is some very precise sense in which gravity, even these interactions that seem very different, they're described by different Lagrangians, different seeming set of ideas, actually have this deep connection. So this is a hidden unity that Lane discovered for decades, but is lying there right under our noses. Okay. So this relation that closed is open squared, that was the first, so again, it starts with this dumbest observation about the spin. Then in string theory, it gets more concrete. The closed is open squared. Now, even for just gluons and gravitons, no strings, nothing like that, we have the kind of relationship that I told you about. But now we're going to talk about the gauge-gravity duality. And here I'm going to back up by reminding you of some big lessons from quantum mechanics, because in a sense, we're going to follow these lessons from quantum mechanics to their bitter end and be led to thinking about these holographic correspondences between different sorts of theories. So here are two of the big lessons from quantum mechanics. First is it's important to pay careful attention to what precise observables are. Okay, so so even though in the classical world we can approximately talk about position and momentum, it's really important, even though it's practically irrelevant for many questions, that in quantum mechanics we can't precisely know what the position is if we know what the momentum is, and vice versa. So the word becomes or and not and. Okay, so it's position or momentum, not position and momentum. And secondly, another lesson that we normally don't emphasize, but has always really struck me, is that there were classical physicists who were tremendously disappointed by quantum mechanics. They couldn't, of course, disagree that it worked, but there are people who thought, there's this Laplacian dream about predicting the future. You give me everything now, I can predict everything about the future. Quantum mechanics represented a drastic, massive reduction from that point of view in the power of physics, right? You couldn't predict anything about the future with certainty anymore. Okay, so other than probabilities, but an infinite number of things that we could talk about before we could no longer talk about. So quantum mechanics implies a drastic loss in the number of meaningful observables. On the one hand, things that we can precisely talk about, the drastic loss in these precise observables. But there is a silver lining, and the silver lining is that if there is many fewer things to talk about, the things that are left have to be related to each other in some subtle way that you missed before. You missed before because you thought they were different and you could talk about different things. There are fewer different things you can talk about. Therefore, the things that are left have to be more closely related to each other than you realized before. So for instance, we lost determinism, but we gained that precisely because of the loss of determinism, we gained that particles and waves can be the same thing. Okay? All right. So we're gonna follow that logic. So first, let's remind ourselves of what quantum mechanics says we're allowed to talk about. In quantum mechanics, in order to talk about any exact observable, we have to do two things. Because the theory is probabilistic, we have to make infinitely many measurements in order to extract the probabilities with infinite accuracy. I want to talk about something precisely. So that's one infinity. The second infinity is we have to do the experiment with an infinitely large measuring apparatus. And the reason is that any finite measuring apparatus itself has quantum mechanical fluctuations. And so, there's a systematic uncertainty to any observable associated with it. Okay? So, for instance, if I'm made out of roughly 10 to the 30 particles. If I try to measure anything, the G-2 of the electron, anything, it doesn't matter. If I try to measure anything to 10 to the power of 10 to the 40 decimal places, so that's very ridiculous, okay? But if I try to measure anything to 10 to the 40 decimal places, there's a problem. Because by the time I get to the 10 to the 10 to the 31st decimal place, 10 to the 10 to the 30th decimal place, maybe I was supposed to write down 7, but me as a quantum system made of 10 to the 30 things, I could have a quantum mechanical fluctuation, I could write down 2 instead. That's one of the more mild things that could happen. Worse, I could tunnel out of the room. I'm not in the room anymore. I turn into a cloud of dust. There's all kinds of things that obstruct me as a finite being knowing anything to accuracy better than 10 to the 10 to the 30. Now, it's ridiculous, which is why we don't think about it. The first infinity with doing the experiment over and over again, there the error is 1 over root n. And so experimentalists care about it. It's called statistical error. And we care about it. The other one goes like e to the n, where n is the number of things you're made of, and so we don't practically care about it. But those are the two infinities that are needed conceptually, to talk about precise observables in quantum mechanics. So quantum mechanics asks you to do this funny thing. You have to drag these infinitely large apparatuses with you everywhere around you go. And it's the correlations between the finite systems and these infinite apparatuses that are given meaning in quantum mechanics. Okay? Now, in a world without, it might be funny, and you might like it, not like it, but it's true. And that's why, in the absence of gravity, in the absence of cosmology, there's nothing funny or weird going on. But, you see, gravity doesn't like this. Gravity does not like this division of the world into two pieces. The piece that's looking and the piece that's being looked at, because everything gravitates universally. And if you try to do an experiment in this room, some fixed size room, you try to measure anything to infinite accuracy in this room, you can't do it. Because you'll have to make your apparatus bigger and bigger. But if you make it bigger and bigger, it'll get heavier and heavier. And before it gets arbitrarily heavy, it'll get so heavy that it'll collapse the whole room into a black hole. Okay? And then you can only do the experiment a finite number of times before you get killed at the singularity. And so there's nothing in this room that can yield a precise observable. This is amazing. Okay? It's a very simple but deep fact. It was understood by people already in the 60s that there are no local observables. So we went from classical to quantum. The world isn't deterministic. That sucked. Okay, it's probabilistic. Okay, fine. But we have all these probabilistic things we can measure. And now further, we add gravity. Nothing you can do in a fixed size room even makes sense quantum mechanically. So there are no local observables. We lose even more. Gravity and quantum mechanics, we lose even more. So what can we talk about? Well, we have to talk about something which can be measured by these infinitely many apparatuses. Infinitely large apparatuses. All you can do is push these apparatuses out to infinity. So they become infinitely large, but infinitely far away from other things. And they can shoot particles into the interior of the space-time. The particles can bang into each other, and they can go back out where they're measured by things at infinity again. Okay, so this is the only kind of observable that we have left when we have gravity and quantum mechanics. The observables live at infinity. And this was, as I said, appreciated by people like Bryce DeWitt already in the 1960s. Okay? Now, in our space-time is, to a decent approximation, flat space. Of course, it's ultimately cosmological, but to a decent approximation, it's flat space. And these experiments have the additional advantage of being what we actually do, what our experimental friends actually do. We're very close to these experiments, right? These are scattering processes where you send things from infinity, which is the same as 27 kilometers around ring at the LHC, and they go into a small distance and they come back out to infinity, because 27 kilometers is pretty infinite relative to the size of the protons that you're colliding. Okay, so these experiments are the conceptually deep, correct observables when you have gravity and quantum mechanics in flat space. They also happen to be very close to what we do in real experiments, which is why we care about them for many reasons. So those are normal scattering processes in flat space. But this general ideology, though, tells you that the only things that make sense when you have quantum mechanics and gravity, you have to go find some boundary somewhere infinitely far away where you can do the measurements and get exact quantum mechanical results. And 20 years ago, string theorists found an incredible model of the world in a box that, physicists love to put things in boxes. And it's very hard to put something gravitational and quantum mechanical in a box because everything is fluctuating. But they found this world in a tin can, which is, for which this whole ideology can be made very, very precise. So this is this famous picture of the inside of a tin can. Inside the tin can, though, the space is warped, it's negatively curved, it's anti-de Sitter space on the inside, and it's like a tin can in the sense that, on the one hand, if you're inside, the warping of the space means that the distance to get out to the boundary is actually infinite, and so that's good. That's what allows the apparatus to get arbitrarily far apart from each other, arbitrarily big, to have all these observables make sense. But on the other hand, light takes a finite amount of time to go from the center and bounce off and come back. So in a very sort of meaningful sense, it's like the inside of a tin can. And so if you now take this point of view seriously, the only observables can only be measured out on the walls of the box, then it's a natural question to ask, why do I need the inside at all, right? The inside is something that I'm using in my head as a theoretical physicist to try to make sense of the observations that took place from, I can ping the ping the box on the outside and send excitations in and have them come out, but I'm not living inside. The only observations I make start and end on the boundaries of the box. So could it be there's a theory that just lives on the walls of the box that actually gives me the same result as everything that I imagine associated with gravity and strings and everything else like that in the middle? And the answer is amazingly yes. So this is a kind of astonishing sort of hidden unity, as far away, in some ways, quite far from that Ming-Vase picture. That Ming-Vase picture wanted us to think that the gravity forces in the Standard Model, the force of the Standard Model and gravity and everything were sort of unified into this one string. Okay, this is something more radical, more strange, more unexpected, that the gauge forces of the Standard Model could be gravity in disguise, right? Not that you put them together, but that there are different sides of the same coin. Okay? Of course, here it's not gravity in our space-time, but gravity in but gravity in this universe with one extra dimension and this tin can, the inside of the tin can, not just the walls. Okay, but this is an instantiation of this general philosophy. It's sort of forced on us by taking what we can observe in quantum mechanics seriously when we also have gravity, tells us we can go out to the walls, and therefore that's all we can do. On the walls, there's a theory that can live on the walls, and that theory is just a good old-fashioned theory of particles. But the interaction between the particles is so strong that the particles are created and destroyed in such abundance that it's not useful to follow them individually. The collective modes of the interaction of these strong interactions of these particles is equivalently describes the inside of this tin can in one higher dimension. Okay, oops. All right, well, this was upside down. But anyway, let me say in words, you can't see this. I want to say that this has been a huge topic of work for 20 years. It'll go on for more decades still. But I want to point out a kind of a huge tension, at least to my mind, a huge tension between this picture and another picture that we learned slightly earlier in the 90s. So string theorists taught us two things in the 90s. One of them is that there's one master string theory. They're all unified together. There's one giant animal, and that has all these different solutions, and they're all connected to each other. And maybe there's even this gargantuan landscape that connects even more things, metastable solutions, and so on. But there's a sort of big, giant unity, one huge object that sort of unifies all of them. That's one picture. Another picture is that any quantum mechanical theory, and in this picture of the gauge-gravity connection, ultimately it's really any quantum mechanical theory can be, on a boundary, can be thought of as describing some theory of gravity in a bulk of one higher dimension in this sort of holographic way. So one picture is ultra unified, right? One picture, so there's this one master thing and we have all these different solutions. The other one is ultra ununified. It says that every quantum mechanical theory is privately defines its own theory of gravity. And on the face of it, I could talk about each one of them individually, and nothing in our current language tells us how to group together the space of all quantum mechanical theories together somehow, okay? In other words, if you only knew the second point of view, if you only knew the second point of view between quantum mechanical theories and gravitational theories in ADS spaces, I think it would be a big shock to you if someone told you there is a master theory in the interior and all these different things that you're talking about are actually different phases of that one theory. I don't see any reason why that would be expected. So there's some tension between these two points of view, and this is a big speculation. I think it's a speculation a lot of people make, is that there's probably some, in this point of view that's been developed for 20 years, the theory on the boundary is king. This quantum mechanical theory is king, and the kind of space-time description, or the space description, the time is not coming along for the ride. The time that flows on the boundary is the same as the time in the interior. That's very important. But the space kind of comes out as some approximation to the quantum dynamics of this theory. It's conceivable that there is a counterpart to this description that we don't have yet, where here quantum mechanics is king and sort of space is approximate and comes out. And perhaps there's some complementary description to this where the picture of the space on the inside is somehow more obvious, but then likely quantum mechanics will be less obvious in this picture in some hard to define way. But this is a motivation to try to find a way of talking about physics in a way where we're not so slavishly adherent, at least to the grammar and the words that we associate with standard quantum mechanics. Even if we're doing standard quantum mechanics in the end, that it could be that there is some way of talking about the physics in the interior that's more unified, more space-time centered, less manifestly quantum mechanical. This is a wild speculation. It's a speculation that a number of people make from time to time, and I think that it's something that we're going to see more of, and will be made more concrete as time goes on. But I'm out of time, but I want to say what the real difficulty is. The real conceptual difficulties that we have to face are that we know how to put the world in a tin can. Our world is not a tin can, okay? And our world isn't even flat space. Our world is cosmological. And this is the biggest set of problems, I think, and I think many people think we have to confront in physics. It's not clear we're going to confront them this decade, in 50 years. It's not clear when we'll make real progress on them. But our universe is not the inside of a tin can. Not only did it likely emerge from this singularity in the deep past, or the Big Bang singularity, but also it's accelerating today. And that acceleration has huge ramifications. For one thing, we only have access to a finite number of degrees of freedom. There are the regions in the universe that are very far away. No information from them will ever make it to us. What we see out there in the universe today is what we're ever going to see. And that means that for the first time, there's a fundamental finiteness that's shoved on top of our heads. Okay? We cannot make apparatuses arbitrarily big. We can make them enormously big, but we cannot make them arbitrarily big. The whole picture of quantum mechanics, of dividing the world into this infinite measuring apparatus and the finite part being looked at, is not even... There's nowhere we can go. There isn't even a boundary we can in principle go to where we can do that. This fundamental finiteness means that there's something flawed with that entire paradigm. Okay? This is what I was referring to in the very beginning when I said that we might need some extension of quantum mechanics. Now, not saying quantum mechanics is wrong, but this is a situation where quantum mechanics just doesn't know what to do, right? We can't make things infinitely big, so there are no perfectly precise observables of any sort that we can speak of. And that's something that's forced on us by the accelerating universe. So, and of course, the other important thing in cosmology is time. You know, whatever happened, what happened near the Big Bang is very likely the notion of time began near the Big Bang. So we can't just leave time alone. We can't just talk about emergent space, which we're learning how to do very well in this world in a tin can holographic picture, but also emergent space and time. And these are the really outstanding challenges for the next decades. All right, so with that, I'm really out of time, so I can't talk about the much more speculative things. That's maybe a good thing. I will leave them up here in the slides if anyone wants to look at them. But actually, maybe I will just, that this is the most speculative thing of all, but since I was just talking about it, maybe I'll just say 30 seconds about it, because it just piggybacks on what I was just saying. As I said a number of times, quantum mechanics forces us to split the world into two parts: infinite observers and finite systems. And we've already seen gravity doesn't like this. Cosmology really doesn't like this. And I actually emphasized a moment ago this one feature that there are no precise observables in when we have the accelerating universe. Something that I find really also disturbing. You see, this is a very, very esoteric thing. This is a very, very esoteric thing, because it means I just told you that I'm made out of 10 to the 30 things, so I can't talk about anything with precision 10 to the minus 10 to the 30. This just extends that to the whole universe. The whole universe doesn't have more than 10 to the 10 to the 120 degrees of freedom, so nothing makes sense to accuracy better than 10 to the minus 10 to the 120. Okay, so you could really not give a crap about this, okay? If you didn't care about you yourself, you care even less about the whole universe. This is another issue, though, where the very similar things come up and where it matters more. For instance, How many of you have thought that, well, one of our big challenges is to understand what happened at the Big Bang, okay? So you might think that, well, what's happened to the Big Bang might have some imprint on things that we could in principle measure. There might be very tiny effects, but they might have some imprint on things that we could actually measure. And if you really imagine doing cosmology, you'd have to put some boundary condition at this singularity moment to be able to calculate anything. And you might imagine that the answers for cosmological correlations that you might measure at late times would depend in some way on the choices you made there. So different theories for what happened there, different choices would lead to differences that you can in principle observe, okay? So there might be really tiny effects, but you might in principle be able to observe them. And that would be true if our universe was not accelerating. Okay? But because our universe is accelerating, because of everything that I told you, because of this finiteness, there is a resolution to, there is a limit to how much we can learn about very heavy physics or very early physics near the Big Bang singularity. And in fact, if you believe in inflation, never mind getting back to the Big Bang, you can ask, let's say there are particles. Let's say there was something stringy going on in inflation. So there are particles, maybe stringy particles are 100 times heavier than the scale, the size scale of the universe during inflation. Their presence or absence would give rise to exponentially small corrections to the correlation functions that we could measure. And you might imagine it's important. There are some consistency conditions on them. They're very small, but they matter. There's some consistency conditions on them. You could in principle measure them. And you could in principle measure them if the universe got big enough that you could get a large enough statistical sample of different regions of the universe to be able to make these statistical measurements to that accuracy. But because of the accelerating universe and this finiteness that we're talking about, there's a limit. And that limit is much more practical than this 10 to the 10 to the 120 that we're talking about. In fact, particles that are just 50 times heavier than Hubble during inflation, we can't even in principle learn about their presence by any experiments we can do in our universe. Never mind what happens at the Big Bang singularity, okay? So all of that stuff, in other words, it's not just, it's hard. The fact that the universe is not infinitely large, we don't get an infinite number of different regions of space, so we can't make we don't get a large enough statistical sample to be able to make these measurements sufficient accuracy, means that all of these exponentially tiny effects associated either with the Big Bang singularity or with heavy enough particles are washed out by quantum mechanics in the late universe, what's called cosmic variance, the fact that we don't have a finite number of samples that we can check. This cosmic variance wipes out any information about very heavy physics, even just 50 times heavier than Hubble during inflation. Never mind what's going on near the Big Bang singularity. This really bothers me. This means that, again, if you take the standard things that we're allowed to talk about in quantum mechanics seriously, it's not even meaningful to ask what happened to the Big Bang. It's a content-free question. It's like asking, well, about the position and momentum of a particle at the same time. This really bothers me. I think this is one of many indications that there is that either we have to live with this, but this is you see, the reduction, now we're taking this really seriously. We have fewer and fewer observables, but now we've finally reached a point where we appear to have no observables at all. And I think the only thing that's left, the only bit of unification that's left that could take care of this is removing this artificial distinction between the system and the observer, this cut between the infinite system and the finite observer. This is incredibly speculative. I have no idea how it will actually eventually happen, but I think if you take this logic to its bitter end, this is where it's pointing to. And I'll just make this last comment before ending. If you think there is something to this, that somehow there is a fundamentally finite system, not infinite. There's a fundamentally finite system, and this finite system gets an interpretation in terms of large observers observing small systems. So there's a way of slicing this finite system up approximately into observers and systems. Then there's at least a vague possibility. There's a vague possibility that while there's something correct about this landscape of solutions in string theory, they all, in some sense, exist as metastable solutions. It may be incorrect to think about them all as literally realized out there somewhere in space in a literal sense. And they might be more akin to different ways of slicing up the same large animal into approximately into observers and systems. So that's very vague, very speculative, but it's something that, that at least gives you a picture for how the part of the landscape which does something useful for you, to even make it possible to find from this one underlying theory universes that look like ours, that part could be true while not foisting on you this ocean of conceptual paradoxes associated with precisely how they're realized out there cosmologically. All right, so that's it. We're going to forget about experiments altogether. But I hope you did get a sense that we're asking quite profound and deep questions in this subject right now. I do think, this was alluded to in my kind introduction, but I strongly believe that it's a singular time in the development of the subject, because the questions are really deep ones. We're not asking about the details of this or that particle or this or that specific phenomenon. We've understood largely many of those things from general principles, even quite remarkably. But we have these more structural questions about the underpinnings of space-time, the origins and fate of the macroscopic universe. And to me, there is increasingly deep and unexpected notions of unification, far beyond the Ming vase picture, far deeper, more unexpected, more surprising, some disquieting, some welcome, some hated, but all carrying this idea of unification beyond what we imagined 30 or 40 years ago. And all I can say about it for myself is that it's clear any human prejudice we have ahead of time for what the answer looks like is just going to be a hindrance to progress. We should just study the things that are deeply tied to these general principles and follow them. Not have a demand ahead of time what the answer should look like, but follow them where they lead us. And more of these things are being uncovered in our theoretical exploration of field theory and string theory. I didn't have any chance to say it, but we definitely need more input from experiments from the LHC, continuing cosmological observations, a whole new frontier of small-scale experiments, but in a colloquium twice as long, I would talk more about these things. But I do think it's an exhilarating time to be doing physics. I just wish I was 20 years younger, because I don't know if real progress on these things will, final level progress even on parts of these problems will happen in 10 years, but they might happen in 20 or 30, and I would rather be 20 or 30 years younger so that I would live to see the end of some of it. But anyway, it's really a perfect time to be 25 years old. So thanks a lot.
Okay, thank you, Nima. So Nima's talk is over, but the real challenge starts now. We have to take him to the airport on time.
Yes.
So I will allow only one or two very quick questions.
Hi, so my question has to do with this thing that you were emphasizing a lot on, the fact that the requirement to measure something with infinite amount of precision.
Yes.
But why do you exactly want it? Why aren't you happy with, let's say, 13 or 14 decimal places? And also, does this have something to do with the fact that space-time is quantized, or if it is not quantized and it's continuous, then you don't even have a problem of creating more stuff? Because, if you think of like all the... Okay,
I got the question. So let me say the first part. It's a fact about the history of physics that it's been very useful to think about what the precise observables are, because the precise observables are what some mathematical theory for the world should be about. Okay? Exactly what you said, you could also say about classical physics. Who cares that you don't know position and moment? Who cares about the uncertainty principle? To much better accuracy than 14 decimal places. For you and me and baseballs and soccer balls and so on, we know the positions and momenta of particles at the same time. But it's important conceptually to know the things that have precise meaning, because that's what a theory should be about. That's what a precise mathematical theory should be about. Now, you might say, maybe for the first time we no longer care about precise mathematical theories. Maybe. But this is taking the 400 years of the logical development of the subject seriously. So that's the answer to your first question. That's why we care about the precise observables, because things that are not precisely observed probably are not part of the underlying equations. And we saw that already most dramatically in the transition from classical to a quantum. For the second question, one of the remarkable things is that we know for almost, I alluded to it already, we know for almost sure that this picture of a quantization of space is wrong. It can't be that what's going on is like, atoms of space and time, where you go down, the surface of the table looks smooth, but then you see it's made out of molecules and atoms. That cannot be what's going on with the space-time, because any such picture of any discrete structure would break Lorentz invariance. It chooses a frame. The table chooses a frame, okay? The vacuum of space-time does not choose a frame. Or said another way, those atoms, the discrete structure better be small, but in whose reference frame are they small? Okay? So if it was something like atoms of space-time, the subject would be vastly less interesting, because then, okay, something like that's going on, and until you got to very high energies to see what that lattice looked like, you could imagine a million different ways it could look, and it wouldn't be too interesting to try to speculate about what it looks like. But it's this existence of Lorentz invariance that makes a humongous difference. Okay? So Lorentz invariance kills immediately many of these naive ideas about space-time, about quantization of space-time. But even in putting that aside, if it was like a little lattice and the universe was expanding, then it's not like it's like you're stretching it out. In that picture, what will be happening, even if you ignore this thing about Lorentz invariance, it's like as you stretch out, then all of a sudden some new atom is born that wasn't there before. You stretch out, some new atom is born, some new atom is born. Classically, the expanding universe, you really think of as more space being created all the time. And if there's this sort of quantization that you're talking about, then as you double it, then poof, another site has got to appear in the middle, another one's got to appear in the middle, and so on. And so they're sort of coming out of somewhere, okay? And we don't know where they're coming from. But
okay,
as I said, the remarkable thing is that these very long distance things come from very short distance things and eventually go back to being very short distance things again. Yeah.
So unfortunate as it is, I'm cutting it down now.
Okay.
So at this point, let's thank Nima for this beautiful talk. Thank you.